Today we're going to discuss the transverse gradiometer as a UXO locating tool. This study was performed for the U.S. Navy in Oahu at Pearl Harbor. And the data was collected using our G882 transverse gradiometer, which is shown here. What I'm going to discuss today is how the data was collected and how the data was processed. And we think it's an exciting way of locating UXO and providing more information about target characterization. So I'm going to start today by talking about the actual data acquisition. And we can see here that this is a section of Pearl Harbor. It's approximately 2 kilometers by 1 kilometer. The data is collected on parallel lines with the transverse gradiometer providing 2 data sets per line. And as you can see here, that each of these lines contains 2 magnetometer traces. So the first thing we do is we plot out the magnetometer trace data to make sure that we have all of the areas covered and that we have done a sufficient distance beyond the area that we're interested in. You'll also see that we did a transverse transect, which is used then to level the data. So that's usually a good idea, and we have tools in the software to do that leveling. So essentially we collect the data. This was collected over a period of 2 days. The survey lines are approximately 10 meters apart, and we were in approximately 7 meters of water. So the altitude off the bottom was between 5 and 7 meters. The transverse gradiometer has depth sensors in both fish and also has an echo sounder altimeter so that we know the altitude of the TVG above the seafloor at all times. This is used then to help in the processing of and the characterization of the targets. So to start talking about the data processing, I want to talk about the first data processing path, which is to apply diurnal correction and to create a total field map. Now, we were in an area where there was a magnetic observatory. It's an intermagnet observatory that records the Earth's magnetic field on a continual basis. So we were able to use some of that data for the purposes of diurnal correction. And we then used the data from all of the magnetometer traces and created a total field map. And that's the map that we see here. First, we'll notice that there is geology in the map. We see a high and a low, and we see many different target anomalies on the map. The geology is very clearly expressed here, and that's due to the fact that Hawaii is a volcanic area and these basaltic flows are highly magnetic. So we do see an area of high magnetics and low magnetics, and we see the individual target anomalies located on top of that geology. We also see a large anomaly associated with a wharf area off to the left here. The second data processing path I want to discuss today has to do with the analytic signal. So the G882 transverse gradiometer records data from 2 sensors simultaneously at a 10 Hertz rate. These sensors are separated by 1.5 meters. So we are continuously measuring the transverse gradient from the array itself. We also measure the longitudinal gradient along the track. We do that by measuring along the track and doing subtraction to get the time series. From that, we compute the longitudinal gradient. Having the transverse and the longitudinal gradient and using a fast Fourier transform, we compute the vertical gradient. Having the transverse gradient, the longitudinal gradient, and the vertical gradient, we take the sum of the squares and take the square root of that to get the analytic signal. We call this quasi-analytic signal. Normal analytic signal computations would have the vertical gradient measured. However, we find that there is sufficient information to get good analytic signal maps based solely on the transverse gradient, the longitudinal gradient, and computing the vertical gradient. We have a separate paper analyzing the results of the quasi-analytic signal versus true analytic signal, and that's available from Geometrics upon request. All right, once we get the quasi-analytic signal, the next part of the data processing is to make an analytic signal map. Here we see the quasi-analytic signal map, which is much different than the total field map. What we see immediately is that the geology has been essentially removed. So now we are only seeing the high frequency anomalies associated with targets. And all targets, all anomalies have a positive anomaly. So you'll see only red marks associated with the targets. The purpose of making the analytic signal map is that we get a clarity of where the positions are for the targets, which enables us, for instance, to see that there are linear objects in the data field. For instance, we see that there appears to be a cable or pipe in this area. There seems to be another cable or pipe in this area. There's a cable down here, there's a cable here, and there's a short section of cable here. So we're able to more easily see where the targets are grouping, and we can also tell something about their size and depth simply from the range of the analytic signal positive anomaly.